Welcome to third part of practice problems on combinational circuits. The first question that you can see here is actually one of the topics from the combinational circuits, and I don't remember if I have explained this to you or not when we were studying the adders and subtractors. That's why I have taken this thing here, and we will see how it works. It's a very important circuit, and there is a probability that this question will be asked to you anywhere in your competitive exams or in your college exams. So let's see why it is very important. It can act as a 4-bit adder as well as a 4-bit subtractor. So this is the advantage of this circuit. The single circuit is here, and it can act as adder at a time, and it can act as subtractor at a time. And how we are going to make it adder and subtractor, that we have to see now. And before actually going into that, let me tell you that this one here is my C in, and it is the thing which decides the performance of the circuit, that how it is going to perform. Is it going to do the addition or the subtraction? So let's start our analysis with these XOR gates that you can see here. I'm having 4 XOR gates for the 4 bits here, and one of the input to this XOR gate is always 1. You can see this 1 is going in this XOR gate here and here. So what will happen to the output of this XOR gate, that we have to see now. And you already know I can write XOR operation as A complement B or B complement A. Now let's say one of the input is 1, always high, so B is always high. Now my equation here will be A complement, 1 complement, 1 and A complement. Now the complement of 1 is 0, and if I take AND operation with 0, I am having 0, and the complement of A is A complement, and ANDing it with 1 gives me A complement. So finally I am having A complement. So you can say that it is acting as a NOT gate. Whenever you are having one of the input to the XOR gate as 1, it acts as the NOT gate. That's why we call it as a controlled inverter. It is a different thing, you already know these things. So at this point I'm having x3 complement, here I'm having x2 complement, at this point x1 complement, and at this point I'm having x0 complement. So this is what we are getting as the output of the 4 XOR gates. Now this is a 4-bit parallel adder, so definitely it is going to add the corresponding bits. It is going to add x0 complement with y0, x1 complement with y1, and the same operation will be done with the last 2 bits. What actually is happening here, the y0 is added with the x0 complement. Now what do you mean by this thing? It is a very important thing for me to explain right now. This is actually the subtraction. Why I'm calling it a subtraction? Because if you remember from the complement presentation, I explained you, if I take the 2's complement, this is 2's complement, and add it with any number, it is equivalent as subtracting the same number. Okay, it means that if I take the 2's complement of x0, that is my x0 dash, and if I add it with y0, it is equivalent as subtracting x0 from y0. This is very important thing. I will write this thing down for you. Adding 2's complement is equivalent as the subtraction. This is something you have to remember always when you are in digital electronics. So what actually this circuit is doing, it is now subtracting. We are getting y0 minus x0, similarly y1 minus x1, and y2 minus x2, y3 minus x3, and whatever be the results here is the output z. So I can say that the circuit is working as the subtractor, and option B is correct, y minus x. Now if I want this circuit to work as the adder, what I have to do? I have to just make this 1, the value of C in, equal to 0. So all these ones will become 0. Okay, and when there is an XOR operation and one of the input is 0, you will find that the output is the variable. What I mean is that if I'm having A XOR 0, so I'm going to have A only. It's a very simple thing that you can do. So I'm simply having x0 added with y0, x1 added with y1, x2 added with y2, x3 added with y3. So it's acting as a adder when Cn is 0, it is acting as a subtractor when Cn is 1. Now there is one thing that you have to think is that I am taking the 2's complement, okay, and just complementing x0 is not going to give me 2's complement, it is 1's complement. So to make 2's complement I need to add 1. It's very clear, if you need 2's complement, just take 1's complement and then add 1 to it. You can see that I have given this C in here, and this C in goes inside and added with the 1's complement. So in this way we are getting our 2's complement. So I hope this thing is clear to you. If you have any doubt regarding this circuit, you can ask in the comment box, because it is a very important thing. From this presentation onwards, there will be a homework problem for you every time. There will be a problem selected by me on the last of the presentation that you have to solve by yourself and post the answer or the option. ABCD is the option. You can post the answer as well as the option. If you want to explain something about that, you can also do that. So it's a good thing for you to practice. So watch the presentation till the end so that you can have your homework problem. Now let's move to question number 2, and in this case we are having a problem on the multiplexer. This problem I have taken to make you feel that you can solve any problem regardless of its look. By look I mean that if you look this problem in the first sight, you will find it little bit tough. You will think that what you have to do actually in this, because something opposite is going in this. But I just want to show you that it's not the way to approach a particular problem. You cannot say a problem is tough or it is easy until and unless you start solving it. Sometime a small problem will prove to be a tough one, whereas sometime a tough looking problem will prove to be a very simple one. So don't judge the problem by its look, just go and start solving it. I have explained you the digital electronics from the basic to the everything, so that you can solve each and every problem that you will face. So let's move to our question number 2, and first we will read what it says. Consider the circuit shown below. This circuit, the output of 2:1 mux, it is definitely a 2:1 mux, is given by the function g is equal to AC or BC complement. Now let's see what I am having here. The C here is my selector variable, I can see. So C is my selector variable, and depending upon the value of C, the input will be linked to the output. So if C is 0, A is linked to G. So I'm having G equal to A, and if C is equal to 1, this E is linked to G. So G is equal to E. So I can write G as C complement A or E C, and here E is equal to B, so I can write E as B here. Now you can see that A is there when C is equal to 1 and B is there when C is equal to 0. But in this case we have done the opposite, because this is what the common tendency of people while solving the mux. They always consider this thing first. Okay, but it is not like that. You cannot see what is inside the circuit. They are just giving the outputs. The circuit may be reversed. You cannot see that. So you have to check these things before approaching to the problem. So in this case, I have to cut this thing down, and G is equal to B. It means when C is 0, B is linking to G, and when C is 1, A is linking to G, which is definitely a opposite thing or a different thing that we have done till now. But there is no problem doing that. There is no question about these things. So G is equal to A in this case. Now I can write it as C complement B or AC. The same thing will be happen to this mux, because these two are identical one, and what we have to do is to find the value of function f. So f is equal to, this is our selector variable for this multiplexer. This is also a 2:1 mux, and when y is 0, it means y complement, this B is linked to f. Okay, and B is what? B is x. Okay, you can see from here. So x is there, or the G is very simply our C complement B or AC, and you can see that A is what? A is 0. This is 0. So I can neglect this thing, and B is E. So ultimately I'm having C complement E as the input to this mux. Now when y is equal to 1, this a is linked to the output and I'm having c complement e. So let's see what I'm having in my options, and this c is definitely equal to x, so I can write it as x. So y complement x, e x complement y. So option B is correct, you can see. So this is the way to approach the problem. You have to break the norms that you have developed in your mind, that every time whenever the selector variable is 0, you have to link this input. It's not always true, because you're not looking inside this circuit, inside this block, you can say. So this is the second problem. Now there is a homework problem for you. This is the homework problem, and you have to find out the value of x in this case. So solve this problem right away. You have done enough of the multiplexers and it will be a good practice to you. And post the answer in the comment box. You can post the option number A, B, C, D. Okay, so best of luck for this and see you in the next presentation.